Hello everyone, my name is Andrew Dotson. My supervisor slash babysitter for my thesis was Dr. Colm Whalen, and the title of my thesis was A Coincident Study of Electron and Positron Impact Ionization. And what does that mean? First I'm going to need to talk a little bit about what a coincidence experiment is. And what this is where you have some incoming particles with a well-defined energy and momentum directed at some target, some bound target like an electron orbiting an atom, ionizing that atom and making measurements on the scattered particles. Now, there's a lot of insight to be found by measuring the kinematics with these kinds of experiments. So it tells you a lot about how these particles interact with each other. And experimentalists have gotten really, really good at using electrons as those incident particles. So that when you use an electron, so one electron comes in, two come out, you call that an E2E experiment. And like I said, experimentalists have gotten very, very good at this. But it wasn't until last year where the first positron experiment was conducted. So you have a positron coming in, positron-electron coming out. So in order to creating a theoretical framework to describe what you could expect for these positron experiments, these positron coincidence experiments, would be a lot of help. And the way that you can describe that mathematically is through these triple differential cross-sections. So in a triple differential cross-section, you're essentially giving a complete picture of your quantum system. You're making measurements of everything pretty much except for the spin. You can make measurements of the spin, but that's just no concern for these types of measurements. So here we have, let me find out, that's a laser. So we have the scattering angles for the slow particle, the fast outgoing particle, and the energy of the system. Okay, moving on. Now, if we want to describe these, first thing to notice is we can approximate these incoming and outgoing particles as plane waves in terms of sines and cosines. And these plane wave functions are going to be functions of the scattering angle, and any function that's a function of angles theta and phi can be expanded in terms of spherical harmonics. Okay, so now we have a direct connection between expressions for plane waves and these L's and M's that are going to be popping up in a few slides. So when you take just certain terms of the series, what you get is what's called a partial wave. Okay, so and each partial wave is going to be, an eigenfunction that corresponds to that specific L and M. And I'm just trying to motivate one of these grosser equations that's going to be popping up in a few slides. Okay, so well, now this brings us to a little bit of bookkeeping. We need to keep track of all the particles that are moving in and out of this experiment. Now, if we're working with indistinguishable particles like electrons, well, the name kind of gives it away. You can't really tell them apart. So what we have here is we have this particle, this electron coming in, or whatever particle it is. This is the wave function for the atom that it's scattering off of. And in this F case, what we're saying is that this fast incoming particle is going to be the same as the fast outgoing particle when you make a measurement. So that's what you call the direct scattering amplitude, and it essentially corresponds to the probability that you measure the incident particle as the fast outgoing particle. Now, like I said, these particles are indistinguishable if you're looking at electrons, which means you also have to take into account the probability that it's the slow particle when it comes out. And that's what you call the exchange scattering amplitude. Now, my project was more concerned with positrons. How do positrons scatter? Well, one of the great things that simplifies this case is that you can tell a positron apart from an electron, which means that this G term goes to zero because you can fix the experiment such that you can force the outgoing particle to be the fast-moving positron. Okay, so we have the same terms that I just showed you here, and this brings us to what's called the distorted wave Born approximation. So what happens when you put a particle subject to some kind of potential? A moving particle subject to a potential? Well, it can curve the trajectory of the particle. And if you're talking about it in terms of waves, what you're doing is you're distorting the wave. And the means of describing the kinematics of this new distorted wave is cleverly called the distorted wave Born approximation. Okay, so here we have these F, L, N's, all this stuff popping up here in terms of the things that I just described. And because we're worried about positrons, we get some nice simplifications where the G's cancel out. And we're left with just this term here. Okay, cool, so that's a whole bunch of theory. How does it correspond to experiment? Well, you can also measure these triple differential cross-sections. It's not just this theoretical construct, and what my advisor did was he constructed the distorted wave Born approximation for the electron and compared it to results for a 200 eV impact energy for a helium atom, so electron scattering off of helium. And one thing to notice is that they agree really well, and what's interesting about this is he made a lot of simplifications to the DWBA such that things like exchange were completely neglected. And what's interesting about this is after simplifying it as much as he could, you still get this weird peak here. Now this green line corresponds to the projected positron DWBA. This isn't something that's measured, it's something that you are saying could be the case because our electron case agrees so well with the experiment. Okay, but the thing with this is that this green line doesn't have a second peak like the electron case does. So why is that second peak here? Well, due to the simplifications in the DWBA, that led my advisor to believe that the reason for this lies in the elastic scattering off of the atom. So that's this term here. So the particle scattering off of the atom, it being the reason for this second peak here. And that's what I wanted to explore with my thesis, is that a correct hypothesis? So what my job was to do was to calculate the differential cross-sections which corresponded to this elastic scattering term in the DWBA. Okay, so when we take a look at this is the differential cross-section. There's a bunch of stuff in here, but it's a bunch of stuff that we already know, right? K is just the wave number, that's something that's an input to the code. L is just the index summed over. These are just Legendre polynomials. We're going over all of the scattering angles. The only thing that we don't know here are these delta sub L's. These are the phase shifts of the wave function. And the phase shift is just a measure of how much the approximate solution deviates from the free particle solution. So when thinking of it that way, that means that if I want to calculate these phase shifts, I first need to calculate what the wave function is. I need to solve the Schrodinger equation for a given potential. So a good test to see that my code is robust enough to handle this kind of problem, I wanted to calculate these phase shifts for a problem that we can already know the answer to the things that we can already measure. So that's what I did. So the next step was using a static potential as my test case for solving the Schrodinger equation, solving it for the hydrogen atom for both an electron and a positron subject to these perturbing potentials, and calculating it and comparing it with results that we already know and love. And from here, the n corresponds to the values that I calculated. I used Numerov's method for calculating the values of the wave function, substituting in certain values of the wave function and comparing them to each other, allowing you to get the values of the phase shift. So the B are from a certain paper by Branston, and there's pretty good agreement with these. The error is on the order of the step size that I used for the code. Cool, so my code works. So that means that since I can rely on my code that was written in Python to give me accurate values of the phase shift, I can use it to calculate values of the phase shift for the things that we don't know now. Okay, what I used it for was for the case where, oh yeah, cool, success. So I used it for the case where I used a 100 electron volt impact energy, and the atom that I was using was hydrogen this time, not helium. So I calculated the phase shifts for this, then used that to calculate the the differential cross sections, and this is the results that I got. What we can see here is that close to a 0-degree scattering angle, the electron and positron elastic scattering are pretty close to being the same. This is a log scale, so we're looking at orders of magnitude. So these are pretty close. And that's something that you can expect. If you shoot an atom head-on with a high enough energy, it's not really going to matter the sign of the charge. It's still going to have the same scattering effect. Okay, and then as you increase the scattering angle, these differential cross-sections start to diverge from each other. And this ratio of electron to positron differential cross-sections approaches about a factor of 2 difference, meaning that the differential cross-section for the electron becomes about 2 times higher amplitude than the positron case. Now you might be thinking, less than a factor of 2 doesn't sound like a lot. And that's because it's not. But if we look back at the helium case here, this secondary peak that we're so interested in is 4 orders of magnitude smaller than the binary peak here. So this less than a factor of 2 difference more than likely is the cause for this secondary binary peak, or secondary peak. And what this means is that for large angles, just to make this actually physical, instead of just code giving you numbers, is it tells you that an electron at higher scattering angles is more likely than a positron to scatter off of an atom and ionize the atom. So you're shooting it at a large angle, it's hitting the atom, scattering off of that, and then ionizing it. What I'm saying is that an electron is more likely to do that, roughly twice as likely to do that than a positron is. Now there are some things that are yet to be explored for this. For example, once these electrons and positrons are actually free particles now, they can still interact with each other. And the Coulomb force from the atom can still interact with it as well. And that's something that hasn't been explored as far as how that affects this secondary peak. Now that doesn't change the fact that the electron, or that the elastic scattering does contribute. All it's saying is that there could be other things that influence it as well. If we had a little bit more time, we could have studied the final channel a little bit more, but that's why we do these senior theses every year, so that maybe a future student can explore that avenue. Thank you guys very much.